Let's, before we get into the whole systems of linear equations, let's just kind of go back for a minute and talk about solving a different, I should say, systems of linear differential equations. Let's go back and just look at kind of probably the most well-known differential equation you've ever seen, which is the following. The derivative of x with respect to t is equal to some constant times x. What makes that a differential equation? Because it's an equation that has a derivative in it. So any equation where you see a derivative, or I should say a function and one or more of its derivatives, that's a differential equation. I should point out, typically in this class, x is what we call the function for some reason. So we're thinking of like x of t as a function. But you might also have seen this in another class at one point as something like dy dx equal to k times x. These are really the same differential equation. Sorry, no, they're not. I'm a big liar. Apologies. Equal to k times y. I am sorry about that. So here's what this says, right? Both of these say the rate of change of your function is a multiple of your function. Or in other words, the rate of growth is proportional to the population size. That's what both of these differential equations say. And we have seen in the past the solution to this differential equation. So I'm going to write it this way. The general solution, well, actually, let's do the process because it's good to kind of see how to do this. So if I'm going to solve this, we can solve this by separation of variables. So bring all my x's to the left. So 1 over x times dx. Bring all my other variable t to the right, a times dt. And then we're going to integrate both sides. With the integral of 1 over x dx equal to the integral of a dt. All right, what's the integral? I know it's been a while. What's the integral of 1 over x? Yeah, ln of the absolute value of x. But yeah, essentially ln of x. We don't really worry about the absolute values in this situation. And then on the other side, the antiderivative of a constant is just that constant times your variable plus c. And then we can solve this by exponentiating both sides. So we can say e to the natural log of x is equal to e to the at plus c. And I want to show you something that happens a lot with this. When we simplify e to the a times t plus c, a couple things happen. One, well, first of all, the left-hand side is just x, right? E to the natural log of x is just x. Or we're going to say x of t. E to the at plus c is e to the at times e to the c. And then we typically call this a new constant, capital C. So we usually end up writing our solution here. And I should point out the solution to a differential equation is a function. Right? We're asking what function meets this criteria. The solution is that the function x of t is c e to the a times t. Or maybe more familiar from your time spent solving exponential growth and decay problems, if you're solving dy dx equal to ky, your solution is y equal to c e to the k times x. Or if it's t, y equal to c e to the k. And I should point out, this really does work. Right? If you actually take your solution to your differential equation and try to differentiate it, well, if we take x of t equal to c e to the at, and we find the derivative, dx dt is equal to, well, we know how to differentiate, sorry, you can't see that, how to differentiate c e to the at. It's going to be c times the derivative of e to the stuff is e to the stuff times the derivative of the stuff. But look, that's exactly my function, x of t times a. So this really is a times x. Or dx dt equals a times x. So this is we're not going to get super deep into solving all sorts of other differential equations, although that's something people do in other classes. This is the only differential equation we really care about in this class, is that when you're solving dx dt equal to a multiple of x, you end up getting exactly c e to the a times t, where that multiple is. That is your solution right here. Just a couple things to say about this, because I do see there's a few homework problems here that have to do with this course situation specifically. So if, for example, let's look at a couple examples just to kind of drive this point home here. If we were solving something like dx dt equal to, I don't know, positive 3x, and we also know that x of 0 is equal to, sure, I don't know, let's make something silly like 8. We can solve this system. We can solve this differential equation. Specifically, we can find the particular solution. So first, if this is my differential equation, I want you all to write down the general solution. So write what x of t should equal to. You're not going to be able to fill in all of the constant stuff, right? We know what A is, we don't know what C is. So you should be able to write down something. I'll give you a moment. It should only take a moment. You don't have to do all the work. You just can say what the answer is going to be. I believe that should be our solution, our general solution. So this is our general solution. And it's general because it's the solution regard to kind of any situation. We don't have any initial condition yet that's going to make it more particular. But now we are going to look at the particular situation here where we have this initial condition. And this initial condition basically says you need to figure out what C is. So whenever you're trying to solve a differential equation and they give you some initial condition, your job is to solve for any constant that happens. So we can say, oh, well, if t equals 0, x of 0 is going to be 8. So if I plug in those things here, I'm going to get 8 on the left equal to c times e to the 3 times 0. So that means c is going to equal 8. So then my particular solution is going to be x of t equal to 8 e to the 3t. That's our particular solution. Cool. Questions so far? Yeah. Integrated on the previous page. Right here. So I didn't do any of the work. I said because this has the same sort of flavor as the thing we just did, where we said, oh, if I want to solve dx dt equal to a times x, you can do all the work, but we can also just know, oh, the solution is always going to look like c times e to the a times t. So all I did was I substituted in 3 for a. So I've essentially got, I've got the same sort of equation right here, right? I've got dx dt equal to a times x. And my solution is x of t equal to c e to the a, which is 3 times t, right there. So I'm not doing the integration, although we certainly could. But the point is that this is the only differential equation we're really going to look at in this class. And so we don't have to derive its solution every time we see it. We're just going to be like, oh, well, if you have, dy dx equal to a multiple of y, or dx dt equal to a multiple of x, the solution is always going to be c e to that multiple times t. So whenever we are doing this, we're always just getting, right? If you're trying to solve dx dt equal to a times x, you're always getting the solution is c to the a times t. Now that's going to evolve a little bit when we start talking about a system of two linear equations with two unknown functions. But it's going to be very analogous to what we're doing now. It's kind of similar to how, a lot of it's similar actually, to how like we talked about before when we were talking about like the linearization of a function of two variables, and you get the tangent plane. And it's really just like taking the linearization of a function of one variable and kind of adding on another piece that looks the same. It's going to be very, very similar to that. So when we start solving a system of two linear equations and two unknowns, we're essentially going to get solutions that look like ce to the 3t or ce to the at. There's just going to be another part we're going to add on. It's going to look almost virtually the same. It's kind of cool. We'll get there. Yeah, other questions? Yeah, Erica. First order linear differential. We are not going to see those in this class. Yeah. Separable are the easier ones to predict. Okay, so the other question that I was looking at on your time was just asking kind of a knowledge question. So let's actually look at this again. So if I was trying to solve dx dt equal to, I don't know, let's say negative 42x, or negative 42 times x of t if you prefer. All right, and this could be this could be dy dx equal to negative 42y. This could be dq dt equal to negative 42q. The idea is always that the derivative of your thing is equal to a multiple of that same thing. The derivative of x is negative 42 times x. The derivative of y is negative 42 times y. The derivative of q is negative 42 times q. Right, exactly. So all of these are going to have solutions that look the same. I'm just using different letters. So this one has a solution that is x as a function of t equals ce to the negative 42t. This one is y as a function of x equals ce to the negative 42x. And this one is q as a function of t is equal to ce to the negative 42t. Now, your second question on your homework has kind of what I think is a weird question, so I kind of wanted to help with it because I feel like it's weird. So if my solution looks like this, what could C be? Are there any requirements on what C needs to be? And C could be anything. So here, if we're writing this specifically, so they're right. So they like to use. So if we're thinking here of Q of T equal to CE to the K times T, one answer to what K and C can be is that C can be anything. But what does K have to be? Well, what's the number that's filling the role of K in each of these examples? Right, it's specifically the number negative 42. Okay, but there is one, because the thing is, this question has two different answers. There's one other answer that people often don't think about, which is that, sure, C could be anything. Specifically, C could be 0. So let's see what that means. If C is 0, then that means Q of T is 0 times anything is 0. It's the 0 function. It's 0 for every value of T. So let me ask you, if your function is equal to 0, is its derivative equal to a multiple of itself? In other words, if my function is equal to 0, is this differential equation satisfied? Well, what's the derivative of 0? 0. So is it true that 0, the derivative of 0, is equal to negative 42 times the function 0? Yeah, it is. So the only difference between C being 0 here and C being anything here is if C is 0, then you have that that Q of T equals 0 times e to the, it doesn't actually matter what K is, because no matter what K is, you're still going to get 0. So what I'm trying to point out is this question is kind of funky. Basically, the other half of this question is that if C is 0, then it doesn't matter what K is taking anything. To me, that feels kind of weird. I don't like that answer. It feels not very nice to me, but I believe it is what they're looking for. Just so you're aware, that's kind of what question 2 is getting at. It's not very fun with C, right? So the answer that your function is equal to 0 is a boring answer, right? It's not very exciting that you're like, but it makes sense, right? If your population is 0, then the rate of growth of your population is 0, because you don't have any population to make more population. But that's kind of why that's also a solution. Cool. Okay, so then let's get back to the real story here. Cool. Yeah, we should go this direction. So now is where we should really start to actually really talk about eigenvectors and eigenvalues. Question?
Yeah. So the first one is like when C is anything.
Right. Right. So C can be anything, but if C is anything, K has to be the actual right number that it should be in my example, -42. But the other possibility is that C could be 0, and then it doesn't matter what K is. Nope, there's no other things that can happen. Because your solution is always going to be C equal to the, I suppose I say the solution is always going to be C equal to C e to the KT. So if C happens to be 0, then great, it doesn't matter what K is. And if K is the right number, then it doesn't matter. Okay. So now we're going to take a quick trip to the side. Come back. We need to really kind of make sure we're solid with eigenvalues and eigenvectors. Only of 2 by 2 matrices. Nothing bigger, just 2 by 2s, but we do have to kind of use that a lot in the coming weeks because, yeah, they're going to come up a lot. So let's look at an example like this. The matrix A, -1, 2, -3, 4. It's pretty standard to read a matrix row by row. So from left to right on the top, and then you go down to the next. So I'm always going to be -1, 2, -4. And let's find the eigenvalues. To find the eigenvalues, we typically find them by finding the determinant of A minus lambda times the identity matrix, and then setting that equal to 0. So meaning we're going to find the determinant of -1 minus lambda, 2, -3, 4 minus lambda. And we're going to set that equal to 0. The determinant is always the product of the diagonal elements minus the product of the off diagonal elements. At least I should say everything I'm saying about matrices and determinants is specifically for a 2 by 2 matrix. So there, you can't just do that for a larger matrix. Not that you probably will encounter that, but I don't want you to take what I'm saying and try to apply it to other things later on in your life. You ever see that? All I'm saying for matrices right now is for 2 by 2 matrices. It's harder for bigger matrices. So here the determinant is going to be -1 minus lambda times 4 minus lambda minus 2 times -3, set that equal to 0. And then we're going to simplify it. And often it'll work out to be nice, although not always. Sometimes this is going to turn out to be imaginary solution, which we're going to see eventually here. This one should be nice. We're going to get, let's see, negative lambda times negative lambda squared, minus 4 lambda plus 1 lambda is going to be minus 3 lambda. And then I have a -4 plus 6 is going to be a +2 overall. And this does factors as lambda -1 times lambda -2. So we get our lambda values being 1 and 2. Have any of you heard of the trace determinant method before? Okay. So maybe we'll talk about that eventually if your teacher goes over it. Maybe we will. It's sometimes faster, it's sometimes not. I will mention it here just so you can see it. So I will just point out you already know how to find the determinant of this matrix. The determinant of A, which we often use the capital letter delta for, is equal to -1 times 4 plus 2 times, sorry, not plus, minus, sorry, don't make silly mistakes like that. -2 times -3 is equal to -4 plus 6, which is 2. And the trace of this matrix, so the trace of a matrix, which we often use the Greek letter tau for, is just the sum of the diagonal entries. So in this case, it is -1 plus 4, which is 3. So what I want to point out, because it does make things easier sometimes, is instead of doing all of this work here to find what's called the characteristic polynomial, you can always find this for a 2 by 2 matrix by just saying it's going to be lambda squared minus the trace times lambda plus the determinant. That is always true for a 2 by 2 matrix, which is kind of cool. I feel like that's probably a little bit faster than doing this work here. So this is definitely the same polynomial. It's lambda squared minus 3 times lambda plus 2 equals 0. So if you want to find your quadratic equation that way, totally fine to do it that way. And there are, so I will also say, there are other things we will see as we go on about the trace and the determinant that make it worth knowing. So I would encourage you all to get comfortable with finding the determinant of a 2 by 2 matrix, which is just this times this minus this times this, and also the trace, which is always just this plus this. Not hard things to calculate, but they will come back later and be useful. So let's go ahead and find the eigenvectors. Eigenvalues usually not too bad, right? It's a couple numbers. Sometimes they'll be gross, they'll be fine. Eigenvectors require a little bit more work. So find the eigenvectors, we're going to remember, actually there's two good ways of finding the eigenvectors. So my typical way of finding the eigenvectors is to use the fact that the matrix times the eigenvector should equal the eigenvalue times the eigenvector. And here's what I'm going to say about this. I would say use this if the lambdas are nice. If your eigenvalues are nice, typically meaning integers. On the other hand, if your eigenvalues are not particularly nice, like irrational or imaginary, like we're going to get, sometimes it makes more sense to use the other version of this, which is a minus lambda I times your eigenvector equal to the 0 vector. It's really the same equation, just written in a different way. So I would say use this if your lambdas are gross. And we'll see why a little bit later. I'll show you some examples eventually. But typically, I like to do it this way because it's usually pretty straightforward. So we're going to take our matrix, which was -1, 2, -3, 4, and our eigenvalues, which were 1 and 2, and find both eigenvectors. So each distinct eigenvalue should have its own eigenvector. So for lambda equal to 1, all we're going to do is we're going to take this equation, a times the vector equal to lambda times the vector, and we're going to solve for the vector. So I'm going to write my matrix A, -1, 2, -3, 4. We typically write the eigenvector as having components x and y. I'm going to call this eigenvector v sub 1. This eigenvalue is lambda sub 1. And it's equal to my eigenvalue times the same eigenvector. And our job is to figure out x and y that make this work. I should say our job is to find x and y that are not both 0. I should make it super duper extra clear. 0, 0 is never an eigenvector. Our eigenvector should always have at least one non-zero component. If they're both 0, go back to the drawing board. Something's wrong. Okay, so in this case, what we usually do is we just use the first equation. So I'm going to take my first row dotted with my first column, So it's negative 1x plus 2y equal to 1 times x. That's my first equation. You could also write down the second equation, but you really don't need. I'll write it down in a second here, but let's just solve this. I've got 2y equal to 2x. So I've got y equal to x. And now we get to pick any non-zero numbers for x and y that we want. Typically, the choice is to make the smallest integer value choices you can. So if I was picking, I would pick x equal to 1, and then I would also have to have y equal to 1. So my eigenvector, the usual eigenvector here would be v1 equal to 1, 1. That would be kind of the standard choice. I should point out, any multiple of that isn't 0, 0 is also a valid choice. So you can see people saying the eigenvector was 2, 2, or 3, 3, or 100, 100, or negative 50, negative 50. Any choice for x and y are not 0 and are the same, for example, would be a valid eigenvector. So an eigenvector, what I should say is any multiple of an eigenvector is also an eigenvector of the same eigenvalue. So really, when we talk about eigenvectors, we think of like the eigenline. So actually, I should point out this y equals x is the eigenline, which is an important graphical thing we'll talk about when we start graphing our system of solutions. Okay. And then if you wanted to, you don't need to at all. If we wrote down the second equation, we should get the same eigenvector. So the other equation would be negative 3 times x plus 4 times y equal to y. And you can see that, oh, if you subtract 4y, you get the same thing. Negative 3x equals negative 3y, which exactly leads you to y equals x. So you never need to look at both equations. You can always just look at one equation and solve for x and y. Let's do the other one. So for the second eigenvalue, which was positive 2, we're going to do the same sort of calculation. We're going to take our matrix, negative 1, 2, negative 3, 4. We're going to multiply it by the unknown eigenvector v2 equal to 2 times the unknown eigenvector. And again, we're going to solve for x and y. So let's see. I'm going to have, looking at the first equation, negative 1 times x plus 2 times y now equals 2 times x. So adding x over to the other side, I get 2y equal to 3x. And a couple things. Usually this is where I like to stop, kind of. So at this point, I would stop and say x and y are each equal to each other's coefficients. Because that's the easiest way to find the smallest integers. So I would stop and say, oh, x is going to equal 2, y is going to equal 3. Except you should write 3 instead of y. Does that solve this equation? For sure. My eigenline, if I solve for y equal to 3 halves x is going to be my eigenvalue. For this eigenvalue. So each eigenvalue has its own eigenline. Again, we're not going to get too into them yet, but we eventually will. Erica? I could, yes. So I will, yeah, I would say any multiple of this vector is also a valid choice. So right, you could definitely say, or 1, 3 halves, or negative 4, negative 6, or anything that isn't 0, 0 that floats your boat. And often the standard choice is either to do what you have done and say, I'm going to pick x equal to 1 and y equal to whatever y needs to be, or the other standard way of doing it is to pick x and y so that they are the smallest possible integer values, which I have done here. Which, if you did it this way, then you can just multiply the whole thing by 2 to get back to it. What else? Came to mind I want to say here. Oh, I know what I want to do. So, not that you ever need to, but you could totally check these actually are solutions, right? It is totally 100% true that if you take this matrix and multiply it by that vector, you're going to get 2 times that vector. Let's check just to be absolutely 100% sure. Negative 1, 2, negative 3, 4 times my choice of eigenvector, which was 2, 3, is going to give us negative 1 times 2 plus 2 times 3 And then the second coordinate's negative 3 times 2 plus 4 times 3, which ends up equaling 4 comma 6, which is indeed 2 times the eigenvector 2 comma 3, as it should be. So you never need to check this, but it's nice to kind of see that, oh yeah, we really are getting what we said we should get. We said we should be getting. But yeah, we often prefer to avoid fractions if at all possible. Okay, so why are we talking about this? And also differential. Well, here's where we're going. And here's kind of an example we can look at. Let's look at the following example. Let's let x1 of t equal the population of, say, wolves in a predator-prey kind of situation. I will say typically in these system of 2 equations and 2 unknowns, I should say, no, actually, I should just say 2 equations. Typically, we use x1 of t and x2 of t, or we use x of t and y of t. And some people kind of use one or the other, some people use both all the time. I'll show you both. I mean, it doesn't really matter. So x1 of t is the population of wolves, and x2 of t is the population of deer. And we're going to say that dx1 dt, the derivative of the wolf population, is the rate of growth of the wolf population. So it is the growth rate of the wolf population. And similarly, dx2 dt is the growth rate of the deer population. So these populations certainly depend on one another. If there's not very many predators, then there's going to be more prey. And if there, but then when there's as the prey numbers get really, really big, predators have more food to feed on, and so they start to grow in numbers, and that decreases so so there's kind of this push and pull. Here are the differential equations that represent this system. I have dx1 dt, the rate of change of the population of wolves, or the growth rate of the population of wolves, is equal to negative x1 plus 2x2. And not that we really have to put a whole lot of thought into this, but the idea is that if we have, the bigger the population of wolves get, the less growth there's going to be, because there's going to be so many of them competing for the limited resources. So that's kind of maybe counterintuitive, and maybe it's not really right. I'm just making things up really, but the point is that this is what we've got. Maybe you would say, well, James, there's more wolves, so they should be growing faster. And I think, well, okay, that's how can we do it? But the population of deer being larger is going to be good for the wolves, right? There's going to be more food for them to feed on. Not that deer are just food. Okay. And then similarly, dx2 dt is equal to, what do I got here? Negative 3x1 plus 4x2. So here, we are kind of making the argument that the more deer there are, the faster the growth rate of deer is going to increase, right? If you got more and more deer, they're going to make more and more deer. We're pretending like they're not competing for resources because there's plenty of grass for them to eat. But on the other hand, the more wolves there are, the less growth rate the deer are going to have, because there are going to be more wolves to eat them. So here are our system of differential equations. And what else? I'll say this. Yeah, okay, that's great. Sure. So you could also make the argument, just to kind of go on, if there weren't any deer, we'd have an exponential decay sort of situation for the wolves, right? Look, that's exactly, that's exactly our dx dt equal to negative 1 times x situation, where if we had, just to point out, if x2 were equal to 0, we would get that x1 as a function of time was equal to c e to the negative 1 times t, which would be exponential decay, right? The population of wolves without anything to eat is going to die off real fast. On the other hand, if the population of deer doesn't have any predators, they're going to grow and grow and grow. If x1 were equal to 0, then we would say that x2 as a function of time would be c e to the 4 times t. Growing and growing and growing, unbounded, because there's no wolves to keep them in check. But we've got a system imbalance here. So what is the system looking like? Well, check this out. This whole system here can be expressed more compactly as a system of, as a matrix multiplication here. We can totally write this as the derivative matrix dx1 dt dx2 dt equal to the coefficient matrix -1, 2, -3, 4 times the variable matrix x1, x2. Or as you will see people write, dx dt equal to a times x, where x is a vector and dx dt is a vector. So what's kind of interesting about this, let me see this. Okay. Cool. So pretty much your next homework assignment is kind of just, right, we've kind of covered all the topics of your next homework assignment. Like just, it's not a lot of questions, although you do have worksheets too, right? But your next homework assignment just kind of, right, they're asking you to find some eigenvalues, find some eigenvalues, find some eigenvalues and eigenvectors. And then the last question on your homework assignment is to take a system, rewrite it like we have just done here. So kind of going that way, and then find the eigenvalues, and that's it. It doesn't seem too bad. I feel like you all could probably crank that out pretty quickly. So let's keep moving in the direction of where you're going to be going. We can certainly, we'll do some more practice tonight. We'll do some more eigenvalues and eigenvectors as we go on, but we should talk about more of the meaning because that's where we're going to go, and things do get a little complicated. So here's the idea. The idea behind the solution is this. If the general differential equation dx dt equal to a times x has a solution that is x of t equal to c e to the a times t, just like we saw at the beginning of class today, then it would make sense for this equation dx dt equal to a times x to have a solution kind of like x equal to c e to the a times t. The problem is e to a matrix is kind of a weird thing, right? It is actually something that people define in weird upper math classes. So what we do instead is we replace e to the at with eigenvalues and eigenvectors. So instead of saying our solution that x is equal to c times e to the at, that's not the way to go. Instead, we're going to use the fact that, oh, wait, we know that a times an eigenvector is equal to lambda times an eigenvector. So we're going to rethink or reimagine our solution as x equal to c1e to the lambda 1t times the first eigenvector plus c2e to the lambda 2t and the second eigenvector. You're going to see this 1,000 times. You definitely don't want to memorize. Now, you probably haven't seen it yet in the class. It's totally fine. But this is where things are going. And this is the general solution, meaning C1 and C2 can be anything until you plug in some values to find some particular values. This is the general solution to the equation dx dt equal to a times x. So let's look at our example. So what I said, I really want you all to believe this because it's going to come up so many times. I want you to be confident in the fact that, oh yeah, this makes sense. So let's actually look at the example we've been dealing with and see what the solutions are going to look like. So here's what we've got. Our system of equations, just to remind you, was, I forgot what they were. I wrote them down. It was dx1 dt, dx2 dt equal to, where'd you go? -1, 2, -3, 4 times x1, x2. That was the system we were looking at. And we had already found, right, that's the same matrix we started with, just as an example. We had already found our eigenvalues and eigenvectors to be lambda1 equal to 1, with the eigenvector being 1, 1, and lambda2 equal to 2, the eigenvector being, I don't remember if it was 2, 3 or 3, 2. I think it was 2, 3. Okay. So now we're just going to write down the solution. So our solution is going to be, our solution to that system up there is going to be x of t as a vector is equal to c1 e to the lambda 1 times t, 1 times t is just t, times that first vector, plus c2 e to the lambda 2 times t, times that second vector. Let me write it out a little bit. So this is kind of the way I would prefer to write this out always. But let me show you a couple different ways people imagine this, just so you can see all the ways. So sometimes people like to write this x of t as really the vector x1 of t, x2 of t. And it's equal to, I'm going to still write it this way. I'm going to write it one more way after this. Who's calling me? No one important. Could be someone kind of important. Okay. And then I'm actually going to distribute these things, c1 e to the t into this vector and c2 e to the 2t into that vector and add them together. So I can really write this as x1 of t, x2 of t equal to c1 e to the t plus 2c2 e to the 2t. And similarly, in the second row, c1 e to the t times 1 plus 3 times c2 times e to the 2t. Any one of these ways is a perfectly fine way of writing this. This is probably the way I would encourage you to do it if left to your own devices. Okay, but now here's what I want to show you. I want to show you that this really is a solution for our initial system. Our initial system, which was, in case you want to write it the other way, dx1 dt equal to -x1 plus 2x2, and dx2 dt equal to -3x1 plus 4x2. So all we're going to do to show that this really indeed is a solution to that is to just find all the things. So let's find, so what we're really saying here is x1 is equal to, in fact, let's write it down. Let's not just say it. x1 of t is equal to c1 e to the t plus 2c2 e to the 2t. And similarly, x2 of t is equal to c1 e to the t plus 3c2 e to the 2t. And now what we're going to do is we're just going to look at this first equation and find both sides of it. So let's find the derivative of x1 first. I can differentiate that. dx1 dt is going to equal the derivative of what this is equal to. So it's going to be c1 times the derivative e to the t is e to the t. And it's going to be 2c2 times the derivative of e to the 2t is e to the 2t times 2. Let's compare that to negative x1 plus 2x2. So there's x1. So negative x1 plus 2x2 is going to equal negative this c1 e to the t plus 2c2 e to the 2t plus 2 times x2. So 2 times c1 e to the t plus 3 times c2 e to the 2t. And if we add those together, let's see what happens. Negative c1 e to the t plus 2c1 e to the t is going to equal c1 e to the t. And negative 2c2 e to the t plus 6c2 e to the t, 2t, sorry. Negative 2 plus 6 is 4. And look, this is exactly the same as that. And the same thing would also be true for this equation here. Let's do it to really verify. So for that equation there, we're going to take dx2 dt, so just taking the derivative, dx2 dt is going to equal the derivative of this, which is c1 e to the t plus 3c2 e to the 2t times 2. And the other side of it, negative 3x1 plus 4x2 is going to equal negative 3 times c1 e to the t plus 2c2 e to the 2t plus 4 times c1 e to the t plus 3c2 e to the 2t. And adding things together, I'm going to get, let's see, negative 3c1 e to the t plus 4c2 e to the t is going to give me 1c1 e to the t. And negative 6c2 e to the 2t plus 12c2 e to the 2t is going to be plus 6c2 e to the 2t. And these two things are indeed the same as each other. Okay, so I know I've said a lot, done like a lot of those words here, but here's the point. The point is, once again, to solve a linear system of differential equations, that is dx dt equal to some 2 by 2 matrix times x, or if you prefer writing it out the long way, dx1 dt dx2 dt equal to a times x1 x2. The solution is x of t equal to c1 e to the lambda 1 t times the vector v1 plus c2 e to the lambda 2 t times the vector v2, where of course lambda 1, lambda 2 are the eigenvalues, and the v1 and v2 are the corresponding eigenvectors. That's kind of the whole shebang. Well, not quite the whole shebang, but like the big gist. So when we are solving systems like this, which we're going to do quite a bit of, the solution is this nice thing, which I will say is very analogous to the thing we said at the beginning of class, which was that the solution to dx dt equal to a times x is c e to the at. Same kind of deal. C e to the lambda times t, and then you got to throw in the eigenvector. The same kind of deal. Questions so far? I know it's kind of a lot, but you're going to see it a lot. So like, don't be too freaked out by it. It's going to be okay. You don't typically have to do all of this. I just want you to see that, oh yeah, the thing we found really and truly is a solution. It's the general solution. So at this point, I will mention C1 and C2 could be anything. And later on, maybe today, maybe right now. Yeah, right now. So a lot of the time, what they then ask you to do is to find a particular solution. Meaning, if you have some initial condition, you have to find your constants C1 and C2. So let's do that. So let's pretend that these numbers are going to seem kind of silly. Let's pretend that we were starting off with x1 of 0 is 2. So we have a population of 2 wolves at time 0. And x2 of 0 is 4. We have, a population of 4 deer. What's going to happen? Well, I shouldn't say what's going to happen. I said, let's find our constants. So let's go back to our solution, which I'll remind everybody. Maybe I'll remind everybody. Our solution. Come back. Our general solution looked like that. There. Let's write that down. So we have, I'm probably gonna write it like this. Sure. x1 of t, x2 of t equals c1 e to the t times 1, 1. Sorry, e to the t, that's the t, not the 2. Plus c2 e to the 2t times 2, 3. Okay. So now we're going to use these initial conditions to solve for C1 and C2. And typically it's a situation of having two unknowns and 2 equations and solving for them, kind of doing a little bit of algebra. So just plugging in our values. If I plug in t equals 0, x1 equals 2, x2 equals 4, I'm going to get 2, 4 equal to c1 e to the 0 times 1, 1 plus c2 e to the 2 times 0, 2, 3. Or more compactly, 2, 4 is equal to c1 times 1, 1. So that's going to be c1, c1, and c2 times 2, 3. So 2c2, 3c2. So I have 2 equations. I have the equation c1 plus 2c2 equals 2. I have the equation c1 plus 3c2 equals 4. And sometimes they're pretty easy to solve, and sometimes they're a little more work to solve. This one's pretty easy to solve because you can just subtract the first one minus the second one to cancel out the c1s. So if I subtract these equations from each other, c1 minus c1 is 0 c1, 2c2 minus 3c2 is negative c2, and 2 minus 4 is negative 2. So negative c2 equals negative 2, or c2 equals 2. And then plugging that back into either equation, c1 plus 2 times 2 equals 2. So c1 equals negative 2. So our particular solution is going to be x1 of t, x2 of t equal to negative 2 e to the t times the vector 1, 1 plus 2 e to the 2t times the vector 2, 3. The negative here. Right here? Oh, it came from me. So I said, these are my 2 equations, right? From that right there, my pen's pointing to. I took that. So I took this equation here, and I wrote c1 plus 2c2 equals 2, and c1 plus 3c2 equals 4. But then I see that I have 2 things I want to solve for, c1 and c2, and 2 equations. And so whenever I'm trying to solve a system with 2 unknowns and I have 2 equations, we can either use the substitution method. So you could have done this a different way. You could have been like, I'm going to do c1 equals 2 minus 2c2, and then plug that into the other equation and say, oh, then 2 minus 2c2 plus 3c2 equals 4. Just plugging that in for c1. And then you would get 2 plus C2 equals 4, so C2 equals 4 minus 2. And then you can plug that in up here to get C1 equal to -2. But what I did was I took kind of a shortcut, which was I said, oh, if I have two equations, I can subtract them from each other. The reason I picked subtraction here is because I saw that both equations have the same value, the same constant multiple C1. I said, oh, if I do this equation minus this equation, that minus that is none of those, that minus that is -1 of those, that minus that is -2. I was just trying to take it. Sometimes they're really less nice, a lot less nice than this. You have to work a little harder for it. Yeah, so let's look at a little bit more practice. Oh, there's one. I should say what? Okay, say one more thing. One more thing about this example with no more practice problems. We still got 20 minutes. Yeah. So here's what I want to say about the solution. And the question that a lot of people are going to ask eventually, because really we're trying to look at the biology of this. We're interested in what these solutions really mean, not just doing some math and writing down numbers on paper. So the idea here is, well, this means something. What happens to the populations, x1 of t and x2 of t, as time goes on and on and on? Meaning, what happens? What's the limit as t goes to infinity of each of these? Well, let's look at the first one. x1 of t is equal to -2e to the t times 1 plus 2e to the 2t times 2. Now, let me ask you, which of these two things gets bigger faster? E to the t or e to the 2t? E to the 2t, right? It's like for example, if t was equal to 3, this would be e cubed, and that would be e to the 6th. And e to the 6th is miles bigger than e to the 3rd. So this positive thing is outpacing this negative thing. If you don't like thinking of it that way, another way to go is to factor out the e to the t. So if I factor out an e to the t, I'm left with a -2 plus 4e to the t. And then I can say, oh, as t goes to infinity, e to the t goes to infinity, and 4e to the t minus 2 also goes to infinity. So both of these things are individually going to infinity, and infinity times infinity is infinity. So the population of wolves is getting infinitely large if you let the system go on without intervening in any way. In a similar way, you look at x2 of t. x2 of t is -2e to the t times 1 again, plus 2e to the 2t times 3. And that's also going to go to infinity in the same sort of way. So this is also going to infinity as time goes on. Well, that doesn't seem particularly helpful, right? So what? Both the populations get really big. Is there anything more we can say? Yes, there is. Where'd you go? Other note page? I can say it, but I wouldn't. Fine. Yeah, okay. So what we can really say here is that one of these two pieces kind of overcomes the other piece. So if you let time go on and on and on and on and on, and actually look at these values, if you compare x1 and x2, in fact, if I looked at x1 of t divided by x2 of t, which is this. Oh yeah, this is smart. All right, I said that very convincingly. I'm like, oh yeah. Okay, so as time goes on, oops, you can't see that. Again, this is the population of wolves compared to the population of deer. Well, which thing's going to matter more? The e to the 2t or the e to the t? Right. And also, you can attack this sort of limit, even though I haven't written the word limit, just like you would do something like x cubed plus 5x plus 1 over 2x cubed plus 7x minus 3, by dividing everything by essentially the highest power of your thing in the denominator. So now the highest power thing is the e to the 2t. So check this out. this is going to equal, if I divide everything by e to the 2t, negative 2 e to the t over e to the 2t plus 4 e to the 2t over e to the 2t. There is really something worth seeing here. I'm not just saying words for the sake of it, I promise you. So we simplify this, we get negative 2 over e to the t. Gosh, I keep wanting to write 2 instead of t. It's killing me, sorry. Plus 4 over negative 2 over e to the t plus 6. And as t goes to infinity, this term is going to go to 0, and this term is going to go to 0. So you're left with 4, 6, which is 2/3. But here is what's great about this. I didn't have to do any of this work to see that. All you have to do is look back at your general or particular solution and ask yourself, which eigenvector goes with the bigger eigenvalue? Which was the bigger eigenvalue? What were the eigenvalues? 1 and 2. And the 2 one is the one that is this one because the eigenvalue is right there. So this is the bigger eigenvalue, and this eigenvector 2, 3 indicates the ratio of wolves to deer. 2 wolves to every 3 deer. As time goes on and on and on. This becomes the dominating factor, and this other part becomes inconsequential. Go ahead. So there were 2 eigenvalues. Literally, I'm just asking which number was literally larger, 1 or 2. 2 was larger. So whichever eigenvalue was the bigger eigenvalue, we have, if they're both negative, I'm just going to say, if they're both positive, whichever one's bigger, we'll talk about negative stuff later. But if you have 2 positive eigenvalues, whichever one is the bigger one, that is the thing that's going to dominate and become the overall arching ratio of one population to another. So I didn't have to do any of this limit, divide all this garbage here. I could have just said, boom, there's my bigger eigenvalue, 2 versus, okay, there's a 1 here I didn't write, right? There's a 1 there, right? That's my bigger eigenvalue. So this is the eigenvector that tells us what the population will do over time. Okay. So maybe enough interpretation for today. A lot of interpretation, but this is really what we are doing with it. We're taking this linear system of differential equations. I should point out, let me go back here. Oh, sorry, that's a 1 that I just tacked in there. So those are my eigenvalues. That's a 1 times t, and that's a 2 times t. I'm just pointing out that this eigenvalue is larger than that. And so this eigenvector is the one that tells us about the behavior of the system as time goes on. So what I was wanting to say was that what we're going to see is that whenever you have a linear system of 2 differential equations, and that's what we have here, right? So it's a linear system because each of your x1 and x2 are raised to the first power, and they have nice coefficients, right? And there isn't anything else. There's squares, there's cubes, there's square roots. It's a nice linear system of differential equations. I should say it's a linear system of linear differential equations. Okay. So whenever you have a system like this is how we find the solution. And this is some of the meaning behind it. So in practice, what we're going to be doing a lot of, sorry, I've got things slightly out of order. I'll fix it later. To solve systems like this, what we're going to be doing is finding a lot of eigenvalues and eigenvectors. I should show you one last thing before we do a couple practices. So later on, not today, we'll talk about how you can graph the phase plane for this, or the direction field for this. There's a nice little program that I think I've linked to in Canvas that's pretty easy to use. But if you try to graph this linear system of differential equations, it looks like this. So if you were to start at any point, like let's say we start at the initial condition where we have 1, 2 wolves and 4 deer. Right here. Well, like if I start that way, both populations are getting very, 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 very large in a 2 to 3 sort of ratio kind of way. Every time you go over 2, you're going to go up 3 eventually, right? Not at the very beginning, but as time goes on. On the other hand, if you start somewhere, well, it doesn't really make, so it kind of doesn't make sense to start here because like that's a negative number of wolves and deer. So it doesn't have a good physical interpretation. But if you started here, you would end up going in this direction here. If you started here with 3 deer and 2 wolves, sorry, 3 wolves and 2 deer, the deer don't make it. And there's too many wolves for those deer, and you end up going this way, and oh no, oh no, oh no, oh no. Nobody makes it, right? Everybody dies. Because there's not enough deer, and then the wolves eat all the deer. The equilibrium, at least for systems like this, and this will change as we go on, but for a nice system like this, the equilibrium is 0, 0. And we're going to talk a lot about whether the equilibrium is stable or unstable. This is an example of an unstable equilibrium because if you look at this, all of my arrows are pointing away from it, right? If I started over here, I'm not going back towards my equilibrium, I'm going way away from it. So we're going to talk about later on how we're going to look at the eigenvalues of a system and be able to tell just by looking at the eigenvalues whether the system is stable or unstable, and if it looks like a spiral or a node, or that's kind of a spiral. And it's really neat. It just takes some practice. So speaking of practice, let's actually do some practice. Let's say we've got some other systems like, so as much as it is, whoa, that feels like a little bit. As good as it is to talk about the interpretation, it's also important that we know how to do these things. So let's say we have a system like this. I want to solve the following system of equations. Dx dt equal to x, y dt equal to 4x minus y. And maybe we have some initial conditions, maybe not. X of 0 equals 2, and y of 0 equals 10. We'll probably ignore that, but let's do it anyway. So if I was going to solve the system of equations, the first thing you really want to write down is write down what the coefficient matrix is. So my coefficient matrix A is, I kind of written it weirdly there, apologies. It's just the coefficients of x in the first column, coefficients of y in the second column. So it's 1, oh, there's no y there, so 0, and then 4, negative 1. And this is the best situation you can hope for. If you happen to have a 0 in the upper right corner or the lower left corner, we're all very happy about that because we can automatically say, oh, great, our eigenvalues are lambda equal to 1 and negative 1. Whatever is in the diagonal. If you don't love that I've just said that without showing my work, let me show you the work. So here's the work. Determinant of a minus lambda I is equal to the determinant of 1 minus lambda, 0, 4, negative 1 minus lambda. And here's what I really want you to see. That 0 being in that corner or that corner means that when you find the determinant, you're going to get this times this, great, minus that times that. And if there's a 0 there or a 0 there or both, that's always going to be 0. So you're just going to get the product of these two pieces. And if you're saying I'm going to have the determinant equal to 1 minus lambda times negative 1 minus lambda minus 0, which I'm not going to write down, and then you set that equal to 0, it's real straightforward to see what the solutions are. It's always just going to be setting each factor equal to 0. There we get lambda equal to 1. There we get lambda equal to negative. Very nice. So this does happen relatively often. You should definitely keep an eye out for if the upper right corner or the lower left corner is 0, or as I should say, if either of the off diagonal entries are 0, then your your eigenvalues are always just whatever diagonal entries there are, which is nice. And so then we can find the eigenvectors. So for lambda equal to 1, we're going to set our matrix 1, 0, 4, negative 1 times our unknown eigenvector equal to 1 times our unknown eigenvector. And this situation is always a little bit challenging at first. Be a little extra careful. So if I write down the first equation, my first row dotted with my column, I get 1 times x plus 0 times y equal to 1 times x, which tells me that x equals x, which is true. X always equals x. It's also not very informative. If x equals x, that really means x can be anything. We don't know what y can be then. So we have to, in some situations, we have to go to the second equation we have. It might also not be helpful. Let's find out. So our second equation is 4 times x minus 1 times y equals y. Oh, that's a lot more. So that's going to give me 4x equal to 2y, or dividing both sides by 2 since I can without introducing fractions, 2x equal to y. So that's going to give me the eigenvector, x is 1, y is 2. Typically, whichever so it's very common to call the bigger eigenvalue lambda 1 and the corresponding eigenvector v1. It's typically called the smaller eigenvalue lambda 2. But people just name them however. People will be like lambda 1, lambda 2. They don't care which one's bigger, which one's smaller. It's pretty common to just call them whatever you want to. So let's find the eigenvector for lambda 2. So for lambda 2 equal to -1, we have the same sort of thing. 1, 0, 4, -1 times our eigenvector that we don't know yet equal to -1 times xy. This is the one where things get kind of extra interesting. So if I look at my first equation, I'm going to get 1 times x plus 0 times y equals -1 times x. Or in other words, x equal to -x. Which is not always true. In fact, it's almost never true. When is it true? What does x have to be for x to equal -x? I'll give you a hint, there's only one answer. Let's see, does 1 work? Does 1 equal -1? No, it doesn't. I could make it easier and just, so you don't have to try and solve it this way, although I like solving it this way because it brings out something, but you could just add x to both sides. If I add x to both sides, then I've got 2x on the left and 0 on the right. And now, what does x have to be? Right, x has to be 0. 0 is the only number that is its own negative. -0 does equal 0. 0 is neither negative nor positive. I'm saying it again, 0 is not a positive number, it's not a negative number. To be positive, you have to be greater than 0, which 0 isn't. To be negative, you have to be less than 0, which 0 isn't. 0 is the only one that's in the middle. Okay, that's not entirely true. 0 is the only real number that is neither positive nor negative. Imaginary numbers, we don't really talk about positive. So x equals 0, but I didn't tell me what y was. So let me ask you all. If x equals 0, based on something I said earlier that I was very adamant about, what's the only thing y cannot be? What's the only thing we don't ever want as an eigenvector? 0, 0. We don't want 0, 0. So y can't be 0. But y can be anything else. I'm going to pick y equal to 1. So automatically, if one of your parts or pieces of your eigenvector is a 0, the other piece is whatever non-zero number you want, but we always pick 1. You can pick 2, I can pick 3, you can pick 4, but they're all multiples of each other, right? This is an eigenvector, then so is any multiple of it. So we pick the one with the smallest possible integer value. I will also mention, if you try to use the other equation to get y equals 1, you won't get that. If we use the other equation, we're going to get 4x minus y equals minus y, and the y's cancel, and you're left with 4x equals 0, which gets you right back to there. So you just have to get real comfortable with the fact that if one of the things equals 0, you have to decide that the other one is equal to 1. Or you could pick 3 if you wanted to, but no one's going to pick 3, right? Your teacher's always going to pick 1. I'm going to pick 1. Everyone's going to pick 1 because we do. So our eigenvectors are, for lambda equals 1, we have the eigenvector of 1, 2. And for lambda equal to -1, lambda 2 equal to -1, we have the eigenvector equal to 0, 1. And not that you're being asked to do this yet, but we could then write the general solution, just so you have some practice. The general solution is going to be x of t, which is x of t, y of t, equal to c1e to the lambda 1 times t times v1 plus c2e to the lambda 2 times t times v2. That is your general solution. I know you're not being asked to do that yet on the homework assignment. It's still good to see it. Okay, I probably shouldn't try to ram another example down your throats.
You think y can be 1 or y can be?
Y can be anything that's not 0. So y could be 2, 3, 4, 5, whatever. Because again, remember what I said before, if once you have something that's an eigenvector, any multiple of it is also an eigenvector. So I'll show you all right here. Let's take a look at take a look at this example for a second. So we just said that for this matrix, if the eigenvalue is -1, that the eigenvector I picked was 0, 1. But you can pick a different one. Let's say, so I'm going to pick, say, 0, 5. Both of these are eigenvectors. Let's check. So you take your matrix. So again, the defining feature of an eigenvector is that when you multiply the matrix by the eigenvector, you end up getting the eigenvalue times that. That's the whole point, is that multiplying the matrix by the eigenvector gives you back just the constant eigenvalue times that same eigenvector. So let's check here. If we do 1, 0, 4, -1 times my eigenvector, I get back 1 times 0 plus 0 times 1. And then 4 times 0 plus -1 times 1. Which is 0, -1, which is indeed -1 times my eigenvector. As it should be. Well, let's now try someone else's eigenvector. It's a multiple of the original eigenvector. Let's see if we do that. 1 times 0 plus 0 times 5 is 0 plus 0. And 4 times 0 plus -1 times 5 is 0 plus -5. And that's equal to the vector 0, -5, which is certainly equal to -1 times the vector that we started with. They're both eigenvectors. And any other non-zero multiple of that vector would also be an eigenvector. And it is the usual standard choice to make your eigenvector have the smallest possible integer values. So that's why I picked 1 here. That's why for the other vector way back when I picked 2, 3, and you said it could be 1, 3 halves. Both of those are correct. The choice I was making is the typical standard choice because we want them just like 4, 6 would also be correct, but I would rather make the choice where the integers reduce as much as possible. So that's usually what we do. If you pick something else, though, it'll be fine. I will say, though, that if there's solutions you're looking at, your answers, some of it will look a little bit different based on if you use a slightly different eigenvector. So I would certainly encourage you all to try to choose eigenvectors that have the smallest possible integers. That's not always possible because sometimes later on, your eigenvalues are going to suck. They're going to be gross things that have irrational components in them. Just happen. It'll be fine then. We don't have too much of that, so it's not too big a worry. But all right, we'll continue talking about this on Tuesday. Your next homework assignment is due next week, right? Kind of wondering when. Like, I feel like the amount of stuff you have to cover to be able to do this next homework assignment seems like it shouldn't take that long in your class. So I'm wondering what y'all are going to be doing on Friday and on Monday because it seems like you might be very, very far ahead of where you need to be to finish this homework assignment. Maybe not. I don't know. We'll see. Keep me clued in. If something crazy happens, let me know. We'll definitely. I plan to talk more about this on Tuesday, and we'll start talking about how we can use these eigenvalues to tell what sort of stability or instability of our system we have, which is kind of